Okay, greetings students. Today we're going to discuss 2.6 in your notebook. So function operations is our objective. A combination of two functions such that the output from one function becomes the input of a second function is called a composite function. Composite. An example. If you have f of x equal to x and g of x equal to x plus 1, you can put one function into the other one, or you could add them together, subtract them, multiply them, divide them. So those are our operations here. So we could do any of these four operations. We can do f plus g of x, f minus g of x. So let's say f plus g of x would be equal to 2x plus 1. A composite. You could also think of it a combination function. Alright, so function operations. F plus g of x is equal to f of x plus g of x. You add the two together. Usually I prefer to add vertically with these and line common terms, like terms one above the other. F minus g of x is equal to f of x minus g of x. F times g of x is equal to f of x times g of x. And then f divided by g of x is equal to f of x divided by g of x. Alright, so what we're doing here is just defining, what do you do when you add, subtract, multiply, and divide functions together. You subtract, add, or you add, subtract, multiply, or divide simply the functions. The domains of the sum, difference, product, and quotient functions, so the domains of these items, consist of the x values that are in the domains of both f and g. So for the domain, you have to be in the domain of both. Also, the domain of the quotient function does not contain any x value where g of x equals 0. So you can't have in the denominator on the division functions a bottom of 0, as per usual. The denominator can never be 0. Alright. So, domains. So example 1a. We're going to take these two functions and we're going to add them together. So we're going to take f of x plus g of x. So let's add them together here. So again, I prefer to add vertically. 2x squared plus 8, that's f of x. G of x is equal to x minus 3. X minus 3. We're going to add these together. Now why did I put the x here and not underneath the x squared? Well, because they don't combine. So I kind of just like to plan it out. If you want to do 2x squared plus 0x plus 8 and then x minus 3, then you're going to have an easier way of lining it up. But here is the sum of the two items, 2x squared plus x minus 3. This is f plus g of x. F plus g of x. I did have a issue here with the parentheses. It should have parentheses around the f and the g there. But it's fine the way it is too. It's understanding that f is a function and we're adding g of x to said function, but I should have put that in the notes like that. So there's f plus g of x. It didn't ask me to actually find, or it did ask me to actually find it, so there we go. There's the f plus g of x. Now for the domain, what we look at here is the domain on either function limited? So we look at f of x, no, this is an unlimited domain. We can put anything in for x. And the same with g of x. It's unlimited domain. And again, to have a limited domain, you got to have a division, or you got to have a square root, things like that. Those are the two main ones. So the domain here, sorry my D looks really weird sometimes for domain. Domain, you could just say it's all real numbers, which the easy way to do that is to do 2 in the R, or you can just say negative infinity to infinity, with parentheses rather. Alright, subtracting the functions. So maybe I'll split this up a little bit differently. So 2x squared plus 0x plus 8. There's f of x. That's f of x. g of x I'm going to put underneath it, and I'm going to subtract. So minus x, and then plus 3. Why plus 3? Well, that's because we are subtracting the whole function. So we're subtracting the x, but we're adding the 3 because we're subtracting the entire value of g of x. That negative distributes to x and to 3. So that's going to be f minus g of x is equal to 2x squared minus x plus 11. There's my composite function. Again, what I did is I subtracted this second function from the first one, g of x from f of x. And my domain again is unlimited. Why is it unlimited? Because there's no value of x that can't be plugged in. And again, my double R looks weird here when I do my double R. You're welcome to put negative infinity to infinity if you prefer for your domain there. So again, unlimited domain because there's any value of x can be substituted in for that particular function. All right. So f times g of x this time. So this time we're going to take and we're going to multiply the functions together. So we're going to take our first function, f of x, 3 of x squared minus 11x minus 4. We're going to multiply by 3x plus 1. I hope it's obvious to you here that we need to distribute the items. So we need to multiply all the items in the first one by the second one, all the items in the first expression by the second expression. So we need to do, it's not FOIL here, it's got more than FOIL, it's got quite a few. So 3x squared times 3x is 9x to the third. 3x squared times 1 is 3x squared. Then we're going to do 11x times 3x plus minus 33x, so negative 33x. So plus a negative 33x. Minus 11x times 1, so minus 11x. And that one was a squared actually. 11x times 3. And then we're going to have here minus 4 times 3x, so negative 12x. Minus 4 times my positive 1 was minus 4. We'll combine these like terms, but in this case, because of the way I've multiplied, they're right next to each other. The 3x squared, the 33x, the 11x, and the 12x. And we'll get 9x to the third. This is our f times g of x. This is not f of g of x, by the way. This is not fog. You can tell by the way it's written, with the multiply sign versus the open O. We'll get to the fog another day. So that's 9x cubed minus 30x squared. Why 30x squared? Because 3 minus 33 minus 23x minus 4. There's f times g of x. And again, my domain is only limited if the domain of the original is limited, or if it's the dividing quotient, if it's a quotient problem. So my domain here is once again, all real numbers, because we can substitute any value in for x on either of these two, and then on this one as well, we can substitute any value in for x. So again, that's what you're looking for. Can you put things in for x? What can you put in for x? What can't you put in for x? Are there limitations? All right, the division, the quotient. So here, we can attempt to factor the first one and see if it factors with a 3x plus 1. It may or may not factor. Now, why is that important? Because if it does factor, then this, when it divides, is going to reduce. So what I'm going to do here is the f divided by g of x. This is equal, the original item is equal to 3x squared minus 11x minus 4 divided by 3x plus 1. But I need to figure out if this numerator factors and reduces with the denominator, if it factors with a 3x plus 1. So I just need to figure out, does it factor with a 3x plus 1? I don't need to figure out what its factors are. I just need to figure out if it has the factor of 3x plus 1. So there's multiple ways of doing that. The main way would be just, factor it, see if its factor is in fact 3x plus 1. So we can do the factoring here with our cross factoring. So 3 times 4, well, that's a negative 12. My goal number is a negative 11. Well, we could accomplish that if we got ourselves a negative 12 and a positive 1. if we had ourselves a negative 12 and a positive 1, we could accomplish that. So it appears like it does factor. Now again, once again, the factoring from here is you have to accommodate that there's an a of 3, so this is not x minus 12 and x plus 1, this numerator. But the a value is 3, so we're going to look at that 3, we're going to say, well, 12 over 3 is the same as 4 over 1. Why 12 over 3? Well, because a was 3. And then 1 over 3, that doesn't reduce. So what does that mean about my factors? That means that my factors are 3x plus 1, or 3x minus 1, 3x plus 1, 3x plus 1 actually. And then this other factor is x minus 4 for my two factors. So I'm thinking here that this is going to factor this numerator with a 3x plus a 1 and then x minus a 4. And again, it's very easy to check your factorings. Just check, do we have 3x squared? Yes, we do. Do we have a minus 4? Yes, we do. And then do we have a minus 11x? A minus 12x plus a 1x is a minus 11x. So my actual f divided by g of x here, because these reduce, is equal to x minus 4. That's my actual f divided by g of x. Now my domain is a little tricky here because the original functions, the domain have unlimited domain, but in the composite function we can't use negative 1/3 for x because that would make the denominator 0, even though that cancels out. Even though we reduced it out when we reduced the quotient here, it still is a number that's not in my domain because it was a number that's not in the domain originally. So domain is x cannot be anything but 1/3, negative 1/3. Those zeros in the denominator, watch out for those, because they are what are called either holes or asymptotes in the domain. In this case, it's a hole. We'll talk about that another time too. Alright, so composition of functions. So here's a little graphical aid to help you understand what's going on here. So the output from the first function becomes the input for the second function. When you combine two functions together to form a composite function. So here's a graphical example. The domain of f is the input of f of x. That becomes the output of f, which is the range of f. Now that then goes into g of x, becomes the domain of g of x, which then makes a new output. So this is what's called composition of function. This is called Fogg and Goff, f of g of x. So this is what we were talking about just a minute ago, and it's going to be on our next page. So this is going with the next items. This is a little graphical aid. So I'll leave that up right now because it goes with this next page, page 79. It goes with this first item here. So this item here, you see this O is not a times sign. It's not filled in. It's not multiplied. It's G-O-F. And it's not actually an O either. It's called a G of f of x. So it's a specialist mathematical symbol here. That means put f of x into g of x. So that means this right here. So it means we have the domain of f of x. It makes a range. That then goes into g of x. Makes a new range out of g of x. So this is what's going on. Domain of f goes in, makes a range. That range goes into g of x, comes out, makes a new range. Alright, so that is what's going to go on in the next group of questions for what's called g of f of x, or Goff, if you called it Goff in Algebra 2. G of f of x, or Goff. So the steps here with this, if you're doing this with numerical values, you evaluate f of x first, then you put that value in to g of x, if we're using numerical values. And it is not commutative because f of g of x does not always equal to g of f of x. So it matters the order here. This one says put g of x into f of x. This one says put f of x into g of x. Very different. They can be very different items. They can be similar as well, but they can be very different at times as well. We're going to talk about that on our first example, example 3 here, about how they're different. All right, this extra space here was for an extra example or something. I'm not going to use this. All right, so this one, what we're going to do here, we're going to evaluate, first we're going to evaluate g of 3. So what this means is f of g of negative 3. So we do this part first, inside. It's very similar to regular parentheses. This is first, right here. We do this first. Contrast that, we're just going to give you 2 different methods to do this. So this part comes first. So we're going to do g of negative 3. So this is method 1 for evaluating composition functions with a number. So g of negative 3, we put negative 3 in for x, is equal to negative 3 minus 4, which equals to negative 7. What we're going to use now is we're going to use this value that we just got, this negative 7, and we're going to do f of negative 7. So why are we using negative 7 instead of negative 3? Well, that's because that's what g of negative 3 gave us. So when we put in negative 3 for x on g of x, we're going to use that output to do my f value. So this is the output that we use. So this is what we used into f of x. So now that goes in for x here. Negative 7 squared plus 2. 49 plus 2 is 51. 51 is my answer. That is f of g of negative 3. 51. All right, method 2. Method 2 involves doing the actual substitution with the x's first and then putting in negative 3. So rather than using the negative 3, we're going to do f of g of x. F of g of x is equal to, we're going to put g of x into f of x here. So x minus 4 squared plus 2. Why x minus 4 squared? Well, because this g of x is being substituted into f of x. So this part here, the x minus 4, replaces the x here on f of x. Again, this whole thing, the whole right side of the equation replaces the x in the first equation. And then what we can do is we can substitute negative 3 in for x now. So f of g of negative 3 is equal to negative 3 minus 4 squared plus 2. This is going to yield the same answer. You can see here that's negative 7 squared, quantity squared, plus 2. Negative 7 squared plus 2, which is the same answer. So there's 2 methods to evaluating what are called composite functions for a number, for numerical value. So if I'm just asking for a numerical value, you can plug it into g of x and plug that number into f of x, or you can do the substitution and then plug the number into the substitution. Method 2 is going to be more efficient when we actually do the substitutions, which is coming up on the next page. So you might want to use method 2 if this is new for you instead of method 1, because method 2 is what we're going to use for the actual substitutions right now. Oh, and I didn't have any actually ones here. In the homework I have a bunch though. So you might have to ask me some more questions on this. Let me look at the assignment right here. I thought we had a few on the f of g of x, but it looks like we don't actually have that many. We don't. We just have numerical ones. Yes, you're welcome to use either method, because on the homework I'm looking at right now, the homework doesn't involve a whole bunch of algebraic expression ones. It just involves substituting numbers in. Alright, let's see if I can make this so it's not over. There we go. So here are our Examples of composite functions. The store is offering us 15% discount on all items. An employee gets a 20% discount. Write composite functions. So what this means is we're going to take 15% off the item, and then we're going to take 20% off the item. So what that means is we pay 85% of the cost. Alright, so our cost is equal to 0.85x, and then we're going to say that the employee also gets another 20% off. Alright, so the employee cost, the employee is equal to 0.85. Now what variable I'm going to use here? I used x on this because this is my price, my original price. So I should define these variables. So let's say this is my price. This is the original price. This is what it's going to cost any person that comes in the store, because the store is offering a 15% discount. They're going out of business or something. They have a 15% discount on everything. So this is the cost for anybody that comes in the store. Now this is going to be the employee's cost. Employees cost. Which variable should I use here with the 0.85? Oh, sorry, that's not 0.85 actually, that's 0.8. Why is that 0.80? Think about that for a second. Why is that 0.80? Because the employee gets 20% off, so they only pay 80% of the cost. So if you're getting 15% off, you pay 85% of the cost. If you pay 20% off, you're going to pay 80% of the cost. And the reason that is because, well, we're taking 15% off 100% of the price. We're taking 20% off 100% of the price. Now this variable I should use here should be the variable of C, because we're going to take the 15% off first and then the 20% off. So I'm going to use a C here, not an X, a C, or whatever variable I decided to use here. So this is my model. And the other model here, if I want to use the same variables, if you want to take the 20% off and then the 15% off, we would say, well, the employee's cost, actually I should probably do this the same way. C is equal to, let's do the 0.8 first, since everybody, and then we're going to do the E equals 0.85 times C. This one falls apart a little bit because the 20% discount, not everybody's getting 20%. So this no longer is the cost for everybody. This is just an initial cost followed by another discount. Alright, so again we have the same variables. Here's the original price. Here's the cost for that, for the employee though this time. And then here's the employee's cost after we take his initial, another 15% off. Alright, so if you were an employee, which discount would you take first and why? So let's figure out which one yields the larger discount. So let's try something simple. Again, with these types of questions, you want to just try something simple. Let's say the item is $10. So is it easier if we take $10 and take 15% off first and then 20% off? Or is it easier if we take $10 and then take 20% off first and then another 15% off? So let's just figure that out. And I should probably grab a calculator since I don't want to do the work by hand, all of it, even though 10 is a nice number. Alright, so once again, here's my old TI-86, my old friend from college when I was in college. You can see here it's got a little bit of food on. There we go. These things last forever, guys, by the way, these TI calculators. So 0.8 times 10 is going to be, well, $8. So if I take 20% off first, it's going to yield at $8. And then 0.85 times by 8 is $6.8, $6.80. So for a $10 item, so $10 item, if we take 20% off first, it becomes $6.80. What if we do, instead of 20% off first, 15% off first? Alright, so let's take that same $10 item, but let's do 0.85 times 10. That's going to be $8.50. And then let's take 20% off that, times by, we can just do 0.8 times by 8.5 instead of having to do the answer thing there. So it's a little bit easier to read. So what's that going to be? $6.80. So it doesn't matter which order we do the discounts in. It doesn't matter. Doesn't really matter which one we do it in. If we do 0.85 times 10 and then do that number times by 0.8, we're going to get the same thing as if we do the 0.8 times by 10 and then times that by 0.85. And that should kind of make sense to you because multiplication is commutative. What does that mean? That means if we multiply by 0.8 first or 0.85 first, it doesn't matter as long as we're multiplying it by both. And we are multiplying by both because we're doing a combination function here. We're putting the one function into the other one. In other words, we're replacing c with 0.85x here or 0.8x here. So we're multiplying 0.85 times 0.8 for a total grand percentage discount of, let's see what our percent discount is, 0.85 times 0.8. 32% off is our total discount. 0.85 times 8 is 0.68. That's 32% off because 68 is 32 less than 100. You can do that too. 100 minus 68 is 32. Or you could say 1 minus 0.68 if you want to use the decimals. 0.32. 32% off. So that is our actual final percentage off, which we did not ask on the question. But that is our percent off total from the original price for the employees. Okay. Ooh, a challenging problem. We all love challenging problems. I'll try to keep this under 35 minutes, guys. So if I start to drag on, sorry. Your teacher offers to give the whole class a bonus if everyone passes the next test. Yay! The teacher says she will give. Oh, it's a girl teacher. I thought it was me. Everyone a 10-point bonus and increase everyone's grade by 9% of their score. You earned a 75 on the test. Would you rather have the 10-point bonus first and then the 9% increase, or the 9% increase first and then the 10-point bonus? So is it more useful to you to add the 10 points and then add 9%, or to add 9% and then 10 points? Well, let's find that out. So let's do 10 points first. So if I do 10 points first, I'm going to add 75 plus 10. That's going to be an 85. And then we're going to take 9% of that. So 85. How would we add 9% to our score? How would we add a 9% increase? It's not saying a flat points increase. It's saying a 9%. I guess the question is kind of, it's clear up ahead on the top what we're asking you to do. It's not clear in the question what we're asking you to do. We're saying 9% of the entire score. So not adding another 9 to this. We're not adding another 9. We're adding 9% of this. 9% of the score. Of the score. So in other words, we're not adding another 9 to that like we did with the flat points. 75 becomes 85. The 9% is not flat points. It's 9% of the 85. So it's kind of on a curve. So how would we do that? We would multiply this by 1.09. Why 1.09? Well, because 9% more than 100 is 109%. So we're taking the score that we got and adding 9% of it to that score. So in other words, 85 times by 9% is another 7 and 65 hundredths. So that's the amount we're adding to the 85. So to get the final value, 85 times 1.09, we're going to assign this person a 92.65%. And if we do instead of the 9% first, if we do the 9% first instead of the points first, so let's do the percent first. So let's do 75 times by 1.09. So 75 times by 1.09 is 81. And then we add the 10 points to that. You can see that our score is a little bit lower. It's now 91.75 instead of a 92.65. And the reason for that is because we're using multiplication on one of our items and addition on the other item. So f of x is, you could say f of x is equal to x plus 10, and g of x is going to be 1.09 times x. So they're different. They're not commutative. It's not both adding or both multiplying like it was on the last one where we're both multiplying. Now, the final thing here, is this the best plan for all students? Should we add before we do our percent increase? And the answer to that question is yes. Yes, yes. We want to add before we multiply because then we multiply by a large number. Adding before multiplication will yield a larger product. So for example, if we're adding 10 or 20 or 30, whatever we're adding, if we add before we multiply and the number we're multiplying by is more than 1, so in this case it's 1.09, we'll always yield a larger product unless the score happens to be a negative score, which we can't have a negative score test. So I guess the counter example to this would be if the score was a negative score, then it could possibly be, no, even then, as long as we're adding, even then if it's a negative score, or as long as we're adding, the product is larger when we add first. Even if the score was negative, if we're adding a positive number, which we're always adding a positive here. Anyway, so that's it for section here, for section 2.6. The homework's on page 82 and 83 and 84. The majority of them are just like what we talked about here. They're just asking you again to find the domain for these functions. Don't worry about the range here for these. We didn't talk about the range on any of these questions. Just asked you for the domain. And remember from last year, some of the students got really confused when we put numbers in the front like this one. We didn't have an example like this. This just means multiply the function by 2 and then add it to the other function times by 3. So multiply first, like this one, 2, multiply by 3, multiply by -2, the whole function. Because I remember last year we had some issues with that. Oh, then these ones on the bottom. We didn't practice these ones either in the notes. So I'll practice number 17 for you here. This means put g of x into f of x, and then f of x into g of x. So when we put g of x into f of x here, that's f parenthesis g parenthesis x, f of g of x. It's going to be 4 times the quantity x squared minus 3, which is equal to 4x squared minus 12. There's f of g of x. And then when we do it backwards, g of f of x, that means put f of x into g of x. So this is going to be the quantity 4x squared minus 3. So notice here I put the 4x into the x for f of g of x, or excuse me, g of f of x. And then for here I put the x squared minus 3 in for x, for f of g of x. Anyway, so this one is 4 squared is 16x squared. This one's 16x squared minus 3. So there's the example of that. I thought that was in there somewhere, and I just barely looked at it. It's not in our notes, so that particular example. Try number 18 too. And then on the back here, you've got your word problems. Good luck. hopefully you do pretty well.